So let's look at a data structure problem involving job schedulers. So job scheduler maintains a list of pending jobs with priorities. Now the job scheduler has to choose the next job to execute at any point. So whenever the processor is free, it picks the job, not the job which arrived earliest, but the one with maximum priority in the list and then schedules it. So new jobs keep joining the list, each with its own priority, and according to their priority, they get promoted ahead of other jobs which may have joined earlier. So our question is, how should the scheduler maintain the list of pending jobs and their priorities so that it can always pull out very quickly the one with the highest priority to schedule next? So this is like a queue, but a queue in which items have priority based on some other characteristic, not on when they arrived. So we saw a normal queue is a first in, first out object. The ones that arrive first leave first. In a priority queue, they leave according to their priority. So there are two operations associated with the priority queue. One is delete max. In delete queue, we just said we take the element at the head of the queue. In delete max, we have to look through the queue and identify and remove the job with the highest priority. Note, of course, that the priorities of two different jobs may be the same, in which case we can pick any one. And the other operation, which we normally call add to the queue, we will call insert. And insert just adds a new job to the list, and each job, when it is added, comes with its own priority. So based on linear structures that we already studied, we can think of maintaining these jobs just as a list. Now if it's an unsorted list, when we add something to the queue, we can just add it to the list, append it in any position. So this takes constant time. However, to do a delete max, we have to scan through the list and search for the maximum element. And as we have seen, in an unsorted list, it will take us order n time to find the maximum element in the list because we have to scan all the items. The other option is to keep the list sorted. This helps to delete max. For instance, if we keep it sorted in descending order, the first element of the list is always the largest element. However, the price we pay is for inserting, because to maintain the sorted order, when we insert the element, we have to put it in the right position. And as we saw in insertion sort, insert will take linear time. So as a trade-off, we either take linear time for delete max or linear time for insert. So if we think of n jobs entering and leaving the queue, one way or another, we end up spending n squared time processing these n jobs. So this is a fundamental limitation of keeping the data in a one-dimensional structure. So let us look at two-dimensional structures. The most basic two-dimensional structure that we can think of is a binary tree. So a binary tree consists of nodes, and each node has a value stored in it, and it has possibly a left and a right child. So we start at the root, which is the top of the tree, and then each node will have one or two children. A node which has no children is called a leaf, and then with respect to a child, we call the parent node the node above it, and we refer to the children as the left child and the right child. So our goal is to maintain a priority queue as a special kind of binary tree, which we will call a heap. So this tree will be balanced. A balanced tree is one in which, roughly speaking, at each point the left and right side are almost the same size. Because of this, it turns out that in a balanced tree, if we have n nodes, then the height of the tree will be logarithmic, because remember that the height doubles with each level. And as a result of which, we can fit n nodes in log n levels provided it's balanced. And because it is of height log n, we will achieve both insert and delete max in order log n time. This means that if we have to add and remove n elements from the queue, overall we will go from n squared to n log n. And another nice feature about a heap is that we don't have to fix n in advance. This will work as the heap grows and shrinks, so we don't need to know what n is. So what is a heap? So a heap is a binary tree with two properties. The first property is structural, which are the values which are stored in the tree. Remember that nodes in a binary tree may have 0 children, 1 children or 2 children. So we could have in general a very uneven structure. Heaps have a very regular structure. When we have a heap, we have a binary tree in which we fill each level from top to bottom, left to right. So in other words, at any point a heap consists of a number of filled levels, and then in the bottom level we have nodes filled from left to right and then possibly some unfilled nodes. The other property with a heap, so the first property is structural. It just tells us how the values look in the heap. So in this node, for example, in this picture, the blue nodes are those which have values and the empty nodes are indicated with open circles at the bottom. The second property about a heap is the values themselves. So the heap property, in this case what we call the max heap property because we are interested in maximum values, says that every value is bigger than the values of its two children. So at every node, if we look at the value and we look at the value in the left child and the right child, then the parent will have a larger value than both the children. So let's see some examples. So here is a 4-node heap. So because it has 4 nodes, we fill the root, then the first level, and finally at the second level we have only one node, which is the leftmost. And notice that the values are correctly ordered. 24 is bigger than 11 and 7. 11 is bigger than its only child 10. 7 has no children, so there are no constraints. Here is another example where the bottom level is actually full. Here we have 7 nodes, and once again at every point we see that 11 is bigger than 10 and 5, 7 is bigger than 6 and 5. So we have the value property, the max heap property, along with the structural property. Here is an example of something which is structurally not a heap. So because it is a heap, we should have it filled from top to bottom, left to right. So we should have a node here to the left of 7 before we add a right child. Therefore, this is not a heap. Similarly here, the node 8 could not have been added here before we filled in the right child of 7. So once again, this has not been filled correctly left to right, top to bottom, and therefore this is not a heap. This particular tree satisfies the structural property of a heap in the sense that it is filled from top to bottom, but we have here a violation of the heap property because 7 has a child which has a larger value than it, namely 8. So our first job is to insert a value into a heap while maintaining the heap property. So the first thing to note is that we have no choice about where to put the new node. Remember that heap nodes are constructed top to bottom, left to right. So if we want to insert 12, it must come below the 10 to the left because we have to start a new level since the previous level is full. The problem is that this may not satisfy the heap property. In this case, 12 is bigger than its parent 10. So although this is now structurally correct, it doesn't have the right value distribution. So we have to restore the heap property in some way. So this is what we do. We first create the node. We put the new value into that node. And then we start looking at violations with respect to its parent. So we notice that 12 and 10 are not correctly ordered. So we exchange them. Right? Now this is a new node. So we have to check whether it is correctly ordered with respect to its current parent. So we look and we find that it is not. So again we exchange these. Now notice that because 11 was already bigger than 5, 12 will remain bigger than 5. So there is no need to check anything down from where we got. We only have to look up. So now we have to check whether there is still a problem above. In this case there is no problem. 12 is smaller than 24. So we stop. So let's add another node. So supposing we add 33 now to the heap that we just created. So 33 again creates a new node at this point. Now 33 being bigger than 11, we have to walk up and swap it. Then again we compare 33 and its parent 12. And we notice that 33 is bigger than 12, so we swap it again. Then we look at the root, in this case 24. And we find that 33 is bigger than 24, so we swap it again. And now 33 has no parents and is definitely bigger than his two children. So we can stop. So how much time does insert take? Well, each time we insert a node, we have to check with its parent, swap, check with its parent, swap, and so on. But the good thing is we only walk up a path. We never walk down a path. So the number of steps we walk up will be bounded by the height of the tree. Now we argued before, or we mentioned before, that a balanced tree will have height log n. So you can actually measure it correctly by saying that the number of nodes at level I is 2 to the I. So initially we have one node 2 to the 0. Then at the first level we have two nodes 2 to the 1. The second level we have four nodes 2 to the 2 and so on. Right? So if we do it this way, then we find that when k levels are filled, we will have 2 to the k minus 1 nodes. And therefore, turning this around, we will find that if we have n nodes, then the number of levels must be log n. So therefore, insert walks up a path. The path is equal to the height of the tree. The height of the tree is order of log n. So insert takes time, order log n. The other operation we need to implement in a heap is delete max. Now one thing about a heap is that the maximum value is always at the root. This is because of the heap property. You can inductively see that because each node is bigger than its children, the maximum value in the entire tree must be at the root. So we know where the root is. Now the question is, how do we remove it efficiently? So if we remove this node, first of all, we can't remove the node because it's a root. If we remove this value, then we have to put some value there. On the other hand, the number of values in the node in the heap has now shrunk. So this node at the bottom right must be deleted because the structural property of the heap says that we must fill the tree left to right, top to bottom. So we're going top to bottom and we have run out of a value. The last node that we added was the one at the rightmost end of the bottom row, and that must go. So we have a value which is missing at the top, and we have a value at the bottom, namely 11, whose node is going to be deleted. So the strategy now is to move this value to 11 and then fix things. Right? So we first remove the 33 from the root. We remove the node containing 11, and we move the 11 to the position of the root. Now the problem with this is we have moved an arbitrary value, not the maximum value, to the top. So obviously there is going to be some problem with respect to its children. So here it turns out that 11 is bigger than 7, which is correct. But unfortunately it's smaller than 24. So to restore the property, what we do is we look at both directions, right? And we exchange it with the largest child. So suppose this had been 17 here. Okay, then we could have swapped 11 with 17 or 11 with 24. Both violations are there. But if we move the smaller child up, then 17 will not be bigger than 24. So we move the largest one. So in this case, we move 24 up. Okay? And now we have 11 again. And now we have to again check whether it is correct with respect to its two children. So again, it is not. So we move the largest one up, namely 12. And then we see now whether it is correct with respect to its children. At this point, 11 is bigger than 10. So we stop. So just as insert followed a single path from the new node at the leaf up to the root, delete max will follow a single path from the root down to a leaf. So once again, the cost of delete max will be proportional to the height of the tree, which, as we said earlier, is log n. So let's do another delete. So we delete, in this case, 24. Now we remove the node for 10. 10 goes to the root. We compare 10 with its two children, 12 and 7, and find that it's not satisfying heap property. So we move the larger of the two up, namely 12. Now we look at its children, new children here, 11 and 5, and again we see it's not satisfying the property. So the larger one moves up. And once it reaches the leaf, there are no properties to be satisfied anymore, so we stop. So one very attractive feature of heaps is that we can implement this tree directly in a list or in an array. So if we have an n node heap, we can represent it as a list or an array with position 0 to n minus 1. So the position 0 represents the root, then in order 1 and 2 represent the children, then 3, 4, 5, 6 are the nodes at the next level, and so on. So just as we said, we filled up this heap left to right, top to bottom, right? In the same way, we number the nodes also top to bottom, left to right. So we start with 0 at the root, then 1 on the left, 2 on the right, then 3, 4, 5, 6, 7, 8, 9, 10, and so on. So from this, you can see that if I have a position labeled I, then the two children are at 2i plus 1 and 2i plus 2. Right? So the children of 1 are 2 into 1 plus 1, which is 3, and 2 into 1 plus 2, which is 4. Similarly, children of 5 are 2 into 5 plus 1, which is 11, and 2 into 5 plus 2, which is 12. So just by doing index calculations for a position in the heap, we can figure out where its children are. And by reversing this calculation, we can also find the index of the parent. The parent of j is at j minus 1 by 2. Now j minus 1 by 2 may not be an integer, so we take the floor. So if we take 11 for example, 11 minus 1 is 10, 10 by 2 is 5. If we take 14 for example, 14 minus 1 is 13, 13 by 2 is 6.5. We take the floor and we get 6. So this allows us to manipulate parent and children nodes by just doing index arithmetic. We go from I to 2i plus 1, 2i plus 2 to go to the children, and we go from j to j minus 1 by 2 floor to go to the parent. How do we build a heap? A naive way to build a heap is just to take a list of values and insert them one by one using the heap operation into the heap. So we start with an empty heap. We insert x1, create a new heap containing x1. We insert x2, creating a heap of x1, x2, and so on. Each operation takes log n time. Of course, n will be growing, but it doesn't matter if we take the final n as an upper bound. We do n inserts each log n, and we can build this heap in order n log n time. There is a better way to do this heap building. If we have the array as x1 to xn, then the last half of the nodes correspond to the leaves of the tree. Now a leaf node has no properties to satisfy because it has no children. So we don't need to do anything. We can just leave the leaves as they are. So we go one level above, and then we can fix all heap errors at one level above. Right? And then again we move up one level above and so on. So we do the kind of up top to bottom heap fixing that we did with the delete max while we are building the heap. So as we are going up, the number of steps that we need to propagate this error goes higher and higher because we need to start at a higher point. On the other hand, the number of nodes for which this happens is smaller. So let's look at this here. So what we are saying is that if we start with the original list of say elements 0 to 14, okay, then the first levels, the numbers 7 to 14 already satisfy the heap property. So whatever values there are, we don't have to worry. So then we go up and we may have to swap this with its children. We may have to swap this with its children and so on. So for 4 nodes, we have to do one level of shifting perhaps to repair the heap property. Then we go up. Now 1 and 2 are the original values, so they may be wrong. So again, we may have to shift it down one value and then another value. So now we need 2 levels of shifting, but we have only 2 nodes for it. So the number of nodes for which this is required is shrinking, is halving actually, and the number of steps for which you have to do it is increasing by 1. So we will not do a careful calculation here, but it turns out that as a result of this particular way of doing a heapify, by starting from the bottom of the heap and working upwards rather than inserting one at a time into an empty heap, actually takes us only linear time order n. A final use of heap is to actually sort. So we are taking out one element at a time, starting with a maximum one. So it is natural that if we start with a list, build a heap, and then do n times delete max, we will get the list of values in descending order. Okay. So we build a heap in order n time, call delete max n times, and extract the elements in descending order. So we get an order n log n algorithm for heap. Now the question is, where do we keep these values? Well, remember that a heap is an array. So initially we have a heap which has n elements. Okay, so we build this heap. Now we said that delete max will remove the element at the top because that's the root. But it will also create a vacancy here. This is the value that will go to the top. This is the last leaf which will go to the top when we fix the delete max. So since there is a vacancy here, we can actually move this to this position. So the maximum value will now go to the end of the heap. But the next time we process the heap, there will be only n minus 1 values. So we will not look at that value. We will just use from 0 to n minus 2. Right? So again, this value will come here. This value will go there. And now we will have 2 elements fixed and so on. So one by one, the maximum value, second maximum value, and so on will get into the same list or array in which we are storing the heap. And eventually the heap will come out in ascending order. So this is actually an n log n sort. So it has the same asymptotic complexity as merge sort we saw before. And unlike merge sort, which forced us to create a new array every time we merge two lists, this is actually creating a list in place. So to summarize, heaps are a tree-based implementation of priority queues in which both insert and delete max can be done in log n time. We can do a bottom-up heapify to build a heap in order n time. And these are trees, but they can be manipulated very easily using an array. Now in this case, we are looking at max heaps. We can also do a dual construction where we change the heap condition to say that each element must be smaller than its children, in which case we have what is called a min heap. And then instead of delete max, the operation we perform is delete min. Everything is exactly symmetric to the other case. When we move something up, we have to move it down according to the min condition. And when we insert something at the bottom, we have to move it up. Right? So the insert and delete min work exactly like insert and delete max, except that the comparisons are reversed because we now have a min condition rather than a max condition locally. And finally, we saw that with a heap, we can do sorting in order n log time in place.